So welcome to the second 2021 Dirac lecture this year. Once again, our speaker is Steve Simon. Before I give an abbreviated introduction, since I introduced him last time, I wanted to encourage people to ask questions. During the lecture, you can raise your hand or type something into chat. I'll be monitoring chat, and Fernando will, and others. And if the question is one that you think it's appropriate, you can also feel free to unmute and ask it. And I also, in particular, want to encourage students to ask questions, both during the lecture and after the lecture. Okay, with that, let me once again introduce our today's speaker, the same speaker as yesterday, Professor Steve Simon from Oxford, who got his PhD from Harvard in 1995, did a postdoc at MIT, spent 10 years at Bell Labs, and then moved across the ocean to University of Oxford, where he's been a professor of physics for on the order of 10 years, I think. And I'll again remind you that Steve has worked in a wide variety of fields of condensed matter physics, correlated electrons, and an overarching theme there. He's worked on many things, but one of the main themes of his research has been topologically ordered states of matter and the connection between those states of matter and quantum computation. And I believe today's lecture is going to be a particularly sort of crisp example of that, where ideas about, as Steve sort of previewed in his previous lecture, ideas from what we know about topological order and topologically ordered matter are being used in, say, quote unquote, more conventional quantum computers to do something called quantum error correction. So I think without any further ado, Steve, please take it away.
Thank you. Thank you for the introduction. It's again, it's a pleasure to be giving this talk. So this talk is going to, well, it won't immediately seem like it's quite a follow-on to yesterday's lecture. It will, by the end, get back to braiding world lines around each other, and you'll see how it connects up. So the first thing we're going to talk about is the idea of a memory, a quantum memory in a computer. So to describe what we mean by quantum memory, we first have to describe what we mean by classical memory. So in a classical memory of a regular computer, the kind you have on your desk, the memory is divided up into bits. Each bit can be in the 0 state or the 1 state. So if you have an n-bit memory in your computer, there are 2 to the n possible states. And if you stop your computer at any point in its computation, that memory of the computer will be in one of those 2 to the n possible states. For example, this is one of the possible, for a 5-bit computer, this is one of the 2 to the 5th possible states that the computer could be in. Now, a quantum memory is a little bit more complicated. Quantum memories are typically divided up into quantum bits or qubits. And a quantum bit is a wave function, which is a linear superposition between a 0 state and a 1 state with 2 complex coefficients out, which we call alpha and beta. So to specify the state of the qubit, you have to actually give, you don't say just whether you're in the 0 state or the 1 state, you have to give these complex coefficients. If you have an n qubit memory, you then have a 2 to the n dimensional Hilbert space, which is an enormous thing to worry about. For example, if you only have 2 qubits, you then have the basis states 0, 0, 0, 1, 1, 0, 1, 1, and each of these basis states needs a complex coefficient. So you have to tell me 4 complex numbers just to tell you the state of a 2-qubit system. So remember this, a 2-qubit system is described by 4 complex numbers. All right, now an error is any process in your computer which changes the state of the memory unintentionally. You did not mean to change the state of the memory, but it changed anyway. So for example, here's a memory of some classical computer, and while we're not paying attention, along comes a daemon and it flips the state of one of those bits, and it just created an error. Now, it may be the case that you have an important piece of information, an important bit of information that you really would prefer that the daemon didn't come along and change. For example, you might be giving this piece of information to a diplomat. And if that bit is in the 0 state, the diplomat is supposed to sign a peace treaty. And if it is in the 1 state, the diplomat is supposed to start a war. And you'd really much prefer if there was no mistakes along the way and no one was able to mess with that piece of information. So what we do is we have the idea of an error correcting code. When error correcting code, the general idea is you have an important piece of information you want to protect. We call that the logical bit, which is either 0 or 1. Then you have several physical bits. In this case, I've used 3 physical bits. These are actual bits storing information. They could be in the 0 state or the 1 state, each of the three of them. But what we're going to do is we're going to either put them all in the 0 state or all in the 1 state. So either 0, 0, 0 or 1, 1, 1. And we call these 2 possibilities the code space. The possibilities which are not 0, 0, 0 or 1, 1, 1, we call them the error space. And whenever we look at our physical bits, we expect to see them either in the 0, 0, 0 state or the 1, 1, 1 state, depending on whether we mean the logical bit 0 or the logical bit 1. Now, let's take as an example the case where we've set our logical bit as 0. So that means we put our physical bits in the 0, 0, 0 state. Now, the way we're going to implement error correction is the following. There's going to be a machine depicted here as a beaver who shows up and looks at the 3 bits. Now, what the beaver is supposed to do is he's supposed to check to make sure that the three bits are in the code space. So either they're in the 0, 0, 0 state or the 1, 1, 1 state. Doesn't care which, he just wants all 3 bits to be the same. So in this case, he sees 0, 0, 0, and he says, oh, okay, you're in the code space. Everything's okay. That's fine. Then he goes away. Then he comes back later, and he checks again. He says, oh, okay, we're still in the code space. Everything's okay. Then maybe in between checks, along comes the demon. The demon flips over a bit. And next time the beaver shows up, he says, wait a second, we're not in the code space anymore. And he knows immediately that the demon has been there and has messed with our information. He says, there's an error. I have to repair this error. And then he tries to figure out what's the most likely thing to have happened while I was away. And looking at this, well, 2 of the bits remain in 0 state and only 1 of the bits is in the 1 state. So the most likely thing to have happened is that the demon came along and changed this bit from 0 to 1. So I can repair it by changing it back to 0. Now all of the 3 bits are the same again. We're back in the code space and we've corrected the error. Now, if the demon was very, very fast, the demon could have managed to flip several of these bits at a time, maybe even all 3 of them, and gone from the code space to a different element of the code space and end up changing the logical bit. He could change from 0, 0, 0 to 1, 1, 1. He would then fool the beaver, and the beaver would not be able to correct that. That would be creating a real logical error. That would be actually changing the logical bit of information. But assuming that the beaver is checking sufficiently frequently and the demon is only able to change 1 bit at a time, the beaver can always arrange to put yourself back in the code space before the demon messes up the piece of information. And that's the way error correcting codes work. If you want to protect your logical bit even more, instead of using 3 bits, you use 4 or 5 or 6 or 7 bits, and you make it much harder for the demon to actually make a logical error, because you'd have to flip many, many bits before the beaver was able to correct. Okay. Now, let's move on to the quantum computer where we're thinking about qubits. Couldn't we do the same thing for qubits? Well, you might say, let's just copy our qubits and the same way we copied our classical bits, and then we'd have some sort of error correcting code for our quantum information. Unfortunately, there's this thing called the quantum no cloning theorem. And it's often credited to Zurich in 1982, although other people have argued that it was something that was known earlier, but I think Zurich was the first person to put it in this language. The statement of the theorem is pretty straightforward, and I'll read it out to you here. Theorem is that given a qubit in an arbitrary unknown state, let's call it phi 1, and another qubit in an initial state phi 2, which you may or may not know, there does not exist any unitary operator U, and all time evolutions in quantum mechanics are unitary operators. So what this means, there does not exist any unitary evolution. There is no way to evolve the system such that the unitary operator applied to the two qubits gives me as an output two copies of the unknown qubit phi 1. In other words, it's impossible to clone the unknown qubit into the register phi 2 and end up as a result with phi 1 and phi 1 in both outputs for all possible input qubits. In fact, you can make the theorem a little stronger. You can even allow there to be some arbitrary phase out front, and you still can't find such a unitary operator. The proof of this is so easy that it's worth doing. So let's do it. The way you prove the no cloning theorem is you suppose such a copying unitary exists. Okay, so suppose we have a copying unitary. What does it do? Well, we can apply it to two states, two basis states, the 0 state and the 1 state. So when it's applied to the 0 state and my register bit phi 2, it produces two copies of the 0 state. When it's applied to the 1 state and a register phi 2, it produces two copies of the 1 state. This is what a copying unitary should do. Now, the thing is, which makes this theorem possible, quantum mechanics is linear. It should act on a superposition linearly. So here we're going to apply the same unitary to the linear superposition alpha 0 plus beta 1. So we apply to the 0 part, we get 0 in both bits. We apply to the 1 part, we get 1 in both bits, and this is the output. Alpha times 0, 0 plus beta times 1, 1. Unfortunately, this is not what we should expect for a copy. A copy of alpha 0 plus beta 1 is alpha 0 plus beta 1 in the first bit and alpha 0 plus beta 1 in the second bit. And these two expressions are simply different from each other. So we conclude that if you have a unitary which copies the 0 bit correctly and copies the 1 bit correctly, it will not generally copy a superposition correctly. So you basically can't clone a qubit. Nonetheless, quantum error correction still exists. And this is due to this guy here, Peter Shor. In this picture, he looks a little bit like Santa Claus. And that's actually probably a good thing because he's really the Santa Claus of this field. He has given us so many wonderful presents. He really created the whole field of quantum computation pretty much single-handedly by two back-to-back extremely important discoveries. The first is the quantum factoring algorithm, Shor's algorithm, invented in 1994, which showed that you can factor large numbers into their prime factors. And once he showed that this was possible on a quantum computer, every government in the world, every spy agency in the world became extremely interested in this and funded quantum computation, because if you can factor large numbers, you can break codes. And then the next year, he showed that it wasn't completely crazy, because he showed that you could correct errors on a quantum computer as well. That made quantum computing a real possibility. So, so we owe everything to Peter Shor, I think. And the version of quantum error correction that I will describe here is due to Alexei Kitaev, and it's known as the toric code. So the remainder of the talk will be describing the toric code in one language or the other, and how it acts as a error correcting code, and also how it is related to topological matter and how it's related to the braiding that I discussed yesterday. So the first thing we need to describe the toric code is a Hilbert space. Our Hilbert space is going to be described in the following way. We take a square lattice and we put on each edge spin 1/2, a two-state system on each edge of the square lattice. So they're marked here as spin 1/2 on the square lattice. We take the whole lattice and we wrap it up into a torus like this, and that gives the name of the toric code, because we're going to put this whole thing on a torus. So it's periodic boundary conditions. Okay. Now the basis states that you can, for the Hilbert space here, we can take as our basis states simply saying that some of the spins on these edges are spin up, and some of the spins on these edges are spin down. So I've chosen to color the spin down red and the spin up blue. We can call those the 1 state and the 0 state if we like. Next thing I'm going to do is I'm going to just do a sort of a trick of bookkeeping, which is going to make our life easier to visualize. And that is, I'm going to color an edge if the spin on that edge is spin down. And I'm going to leave it uncolored if the spin on that edge is spin up. So if you look carefully, you'll realize that the basis state described both on the left and the right are actually the same basis state. Every place where there's a red dot over here, the edge is filled in over here. And when there's a blue dot, the edge is not filled in. So it's just bookkeeping here. Wherever it's a spin down or 1 state, you color in the edge. And where it's spin up, you leave the edge uncolored. Okay. Now, the next thing we're going to need is we're going to need some operators that act on our Hilbert space. The first operator is a pretty simple operator to describe. We're going to call it a vertex operator, and it lives at a vertex operator. You can define it at every one of these vertices. What is the vertex operator? It's just the product of poly sigma z operators for all the 4 edges coming into that vertex. So remember, the poly sigma z operator gives you +1 if the spin is up, and it gives you -1 if the spin is down. So the vertex operator, all it does is it gives you a +1 if there's an even number of down spins or an even number of red bonds coming to the vertex, and it gives you a -1 if it's an odd number. So for example, here, there's 2 red spins coming to that vertex. So the value of the vertex operator is +1 in this state. And here, there's a single, an odd number of red bonds coming into this vertex. So the value of the vertex operator is -1, okay? That's a pretty easy operator to keep track of. Slightly harder operator is the Plaquette operator. So the Plaquette operator acts on the 4 edges of a plaquette, and it's the product of the 4 sigma x operators around the 4 edges of the plaquette. Now you remember the poly sigma x operator takes a spin up and it turns it into a spin down, and takes a spin down and turns it into a spin up. So this plaquette operator, what it actually does is it flips the state of the bits on all 4 edges of the plaquette. So for example, if we apply the plaquette operator here, what it's going to do is it's going to color in the 2 uncolored edges, and it's going to uncolor the 2 colored edges like this, okay? And if I apply the plaquette operator here, it's going to take the 3 colored edges and uncolor them, and the 1 uncolored edge is going to become colored, okay? Now, it's a little harder to see what the eigenvectors of the plaquette operator here are. The eigenvectors of the vertex operator are either having an even number or an odd number of red bonds coming into the edge. Those are eigenstates of the vertex operator, but the eigenstates of the plaquette operator are more complicated. In fact, the eigenstates of the plaquette operator are equal superpositions of a flipped and unflipped plaquette. Why is that? Well, if I apply the plaquette operator to this superposition, the red part, this guy, all of these get unflipped and turned into this picture here, and this guy, all of them get flipped and turned into the, and get turned into this picture here. So the superposition stays unchanged. This one turns into this one turns into this one, and the sum of the 2 stays unchanged under the plaquette operator. So this is a +1 eigenstate of the plaquette operator. And if I put a minus sign in between, it would be a -1 eigenstate of the plaquette operator. This is also a +1 eigenstate, superposition of this one plus this one, because you get from this one to this one by flipping over the plaquette. Similarly, you can get from this one to this one by flipping over the plaquette. And so far, so good. Everyone happy? All right. So where are we going with this? I should mention that if you read the literature, some references, actually including the original reference, exchange sigma x and sigma z. Where I use sigma x, they use sigma z, and where I use sigma z, they use sigma x. I apologize for that. there's a bit of a split in the literature as to which one you should use in which place, but okay. So just use that as a warning. Okay, so now that I have my, my two operators, we want to say a couple things about the operators. Well, they're commuting. That's the first thing we want to say about these operators. Why is that? Well, if the operators are far apart, like one of them is on a vertex over here and one of them is on a plaquette way over here, then they obviously commute because they're not even acting on the same spins. But if they're close together, it's a little less obvious. It should be obvious that the vertex operators commute with each other because the vertex operators are just made of sigma z's, and all sigma z operators commute with sigma z operators. And similarly, the plaquette operators all commute with each other because the plaquette operators are all made with sigma x's, and all sigma x's commute with each other. What's less obvious is that the vertex operators all commute with the plaquette operators, even when they're very close together. And let's see why this is. So let's take, for example, this vertex operator and this plaquette operator. Both of these operators act on this edge here and this edge here, as well as this one that acts over here, and this one acts over here and here. But both of them are acting on this edge and this, they're sharing two edges. Well, one of them, the vertex operator is applying sigma z to the edge. The plaquette operator is applying sigma x to the edge. Sigma z and sigma x anti-commute. However, they anti-commute on one edge, they anti-commute on the other edge as well. So they're anti-commuting on two edges, which means overall they commute. And that mathematical statement is maybe not completely obvious, but there's an easier way to see that these two operators commute, which is just to say, well, it was just to sort of examine what happens to the eigenstate of this vertex when I apply the plaquette operator. So the eigenstate of this vertex is -1 because there's an odd number of red bonds coming to that vertex. Now let's apply the plaquette operator. It flips the two edges, and there is still an odd number of red bonds coming into that vertex. So the eigenstate of the vertex operator hasn't changed. And this tells you that you can commute the vertex and plaquette operator through each other. Similarly, at this vertex, you have a +1 for the vertex operator because there's an even number of red bonds coming in. If you apply the plaquette operator here, it flips two of the red bonds, but still there's an even number of red bonds coming to that vertex. The eigenstate of the vertex operator has not been changed, showing that the vertex and plaquette operators commute with each other. Okay, so now so we have a whole bunch of commuting operators. How many commuting operators do I have? Well, I have exactly as many commuting operators as I have number of spins. Each unit cell consists of 2 spins and consists of 1 vertex operator and 1 plaquette operator. So the same number of spins in the entire system as I have number of vertices plus plaquettes in the entire system. Now, the question you might ask is, do we have really a complete set of operators which will completely describe the state of the system? Why might you think that would be the case? Well, if I want to completely describe the state of the system, I could take, if I have n spins in the entire system, I could specify what is the state of those n spins. Each spin can be either up or down, 2 options for each of the spins. Now, similarly, I have exactly the same number of vertex operators plus plaquette operators. And each of these vertex and plaquette operators can either be in the +1 eigenstate or the -1 eigenstate. So it seems as if specifying the state of the spins is exactly the same number of degrees of freedom as specifying the state of the vertex operators and the plaquette operators. So do I completely specify the state of the system by specifying the eigenstates of the vertex operators and plaquette operators? And the answer is almost. If I tell you all the eigenstates of the vertex operators and plaquette operators, you almost specify the state of the entire system. And the reason it's only almost is because there are not all of V's and P's are independent. They're almost all independent, but not quite independent. And in particular, there's these 2 constraints, that the product of the plaquette operators over the entire system is equal 1, and the product of the vertex operators over the entire system is equal 1 as well. So why are these constraints there? Well, let's look at 2 vertex operators right next to each other. If you take 2 vertex operators next to each other, they apply sigma z's to all of the edges here coming into the vertex, and sigma z applying to all the edges coming into this vertex. Sigma z has been applied twice in this intervening edge, this shared edge between them. Well, sigma z applied applied twice is just the identity. If you square sigma z, you get the identity. So nothing has been done to this one edge in the middle. Now, similarly, if you apply the vertex operator to every single state, every single vertex of the entire system, the product of them all is going to hit each edge twice with sigma z, or ends up just giving you the identity 1. You multiply all the vertex operators together, each edge has been hit twice by sigma z, so it just has to give you 1 at the end of the day. Similarly with the Plaquette operators, apply sigma x. If you take two Plaquette operators on the plaquettes next to each other, they apply sigma x twice to the intervening bond between them, intervening edge between them, and sigma x applied twice, flips over the spin twice. It's just the identity. Sigma x squared is the identity. And so if you apply the Plaquette operator to every single plaquette in the system, sigma x squared is going to be applied to every single edge in the system, or just the identity is going to apply to every edge in the system. So the product of Plaquette operators over the entire system is going to be 1.
Sorry, I have a maybe basic question. So what is the boundary condition?
It's periodic boundary conditions.
Oh, so okay.
Yeah, so that was the first thing I said. Everything has to be on the torus.
Okay.
So it's always periodic boundary conditions. Yeah. Right. So fixing the P's and V's of the entire system leaves exactly 2 degrees of freedom unspecified, because you have, the number of degrees of freedom is the number of spins, which is equal to the number of vertices plus the number of plaquettes. All of the V's and P's are independent except for these 2 constraints. So we have 2 degrees of freedom remaining that we do not specify if you specify the eigenstates of all the V's and P's. Or another way of saying it is you can independently set the eigenstates of all the P's and V's except the last one. The last one you can't set independently because it's fixed by this constraint, and that leaves 2 degrees of freedom remaining that you haven't been able to set. And these degrees of freedom are going to be important because that's where we're going to put our quantum information. We'll see in a moment. So the next step is we're going to construct a code, our quantum error correcting code. So the rules for our code space are as follows. The first rule is we want to specify that every vertex has to be in the +1 eigenstate. So we should imagine in our head that that there's this beaver coming through the system, checking every single vertex as fast as he can to be sure that every vertex is in the +1 eigenstate. If every finds a vertex in the -1 eigenstate, he'll say, wait, there's been an error, something went wrong, okay? And he has to find a way to put you back in the code space. Same as the example I did with the beaver earlier on. Now, what does it mean to have all the vertex operators in the +1 eigenstate? What it means is that there should be an even number of red bonds coming into each vertex, and you'll realize that that basically means that all the configurations are loops of this sort of red string. So this is an allowed configuration. This is an allowed configuration. This is allowed configuration. Everything that you can write down that satisfies this has to look like a set of closed loops. You're not allowed to have endpoints You're not allowed to have endpoints like this one or like this one or triple points like this one. It has to be closed loops like this with an even number of red bonds coming into each edge. The second rule for the code space is that all the Plaquette operators have to be in the +1 eigenstate as well. And if you remember, the rule for being the +1 eigenstate is that the plaquettes have to be an equal superposition of flipped and unflipped, like this one, or like this one, or like this one. So the way we're going to construct something that lives in this code space, it satisfies these 2 rules. And again, there should be a beaver checking to make sure that the Plaquette operators are all in the +1 eigenstate. The way we're going to construct wave functions that satisfy rule 1 and rule 2 is we start with some fiducial configuration, some reference configuration, which might be just a state with no red bonds. and we are going to add to it all the configurations, all the loop configurations that we can reach by flipping over plaquettes. So we'll start with this configuration. We'll start flipping things like this. We'll add it, add it, add it, add it, add it. And we add them all with the same coefficient. And that will give me an equal superposition of all flipped and unflipped plaquettes and only loop configurations, okay? And that will give me something that satisfies rule 1 and rule 2. That's something that's allowed in the code space.
Steve, I'm sorry to interrupt. I think people can still hear you, but there was a sort of a volume decrease that I think I've confirmed at least some other people have heard. I think it's still understandable, but if it's possible to adjust it back to where it was.
Yeah, let's see if I can. Not sure what happened. Oh, yeah. Is that better?
Yeah, that sounds good. But yeah, maybe a little bit. That sounds good. That sounds good.
Okay, good. Okay, so is that too high? That's too high. Is that better?
You can, a little bit lower, but that, that's I think perfect.
Right there. Okay. I don't know why that happened, but okay. All right. So should I back up and repeat what I was saying before?
Yeah, it probably wouldn't hurt.
Okay. Let me back up a little bit. How far back should I go?
Actually, it doesn't have to be that far. I think people could hear. So I'm just to get back into the flow.
Okay. Just go back into the flow. All right. All right. So the point here is that we're going to construct wave functions that satisfy both these rules by starting with a reference configuration and just flipping over all the plaquettes and adding up the results. And that will satisfy both rule 1 and rule 2. Now, we expect that somehow or other, there should be 2 logical qubits remaining where we can put quantum information. And that's because when we fixed the P's and V's, there were 2 degrees of freedom that we left unspecified. And can we identify what those degrees of freedom are? And the way we should identify that is by asking whether a successive flipping of all these plaquettes will obtain all allowed loop configurations. And the answer is no, that you can't get all loop configurations by flipping over plaquettes because you never change the parity of the number of the loops around the handle. So for example, imagine this sort of imaginary green cut across your torus periodically all the way around the handle of the torus. I can flip over plaquettes, add the results together, but when I flip over the plaquette, I never change the fact that this green line cuts through an even number of red bonds. So here it was 2, and then I flip, and here it was 4, and then I flip, and then it's 2. It's always going to be an even number of red bonds I cut through, no matter how many things I flip over. On the other hand, if I had started with a different initial configuration, one like this, where there's a single red loop going around the handle, then I can start flipping over bonds. And if you remember where that green line was here, it will always be an odd number of red bonds going around the handle of the torus. I will always cut through an odd number of red bonds if I draw that green line here, no matter how many things I flip over. So the most general wave function that I can write is going to be a sum of 4 possible wave functions, which is described by the parity of the red loops around the handle. So the first wave function will have an even parity of red bonds going around both handles. Then there'll be an even odd, where it's even around one handle, odd around the other handle, odd, even, odd around the first handle, even around the second, and odd, odd will be odd around both handles. And each of these wave functions can get a separate complex coefficient. Now, if you remember way back when we defined what a qubit is, remember when we had 2 qubits, we had 4 complex coefficients, and that's exactly what we have here. So we're storing our quantum information for exactly 2 qubits of information in the coefficients of these 4 possible wave functions, which are distinguished from each other by the number of red bonds running around each handle. So I can draw the picture a little more prosaically like this. Here's my torus with no red bonds. Then you can have some red loops, but still an even number of red bonds around each handle. Here, there's still an even number of red bonds around each handle. And then here's an even odd wave function with an odd around one handle, but an even around the other handle, and so forth. And the claim is this code space is going to be very good for storing quantum information. Okay. Now, it's obvious, or it should be obvious, that the handle of the torus was absolutely essential to this argument, because we're counting whether things are even or odd around the two handles of the torus. And you might ask whether you could do something with a torus with multiple handles, a G-handled torus, what we call the genus of the object. This would be genus 2. This would be this fidget spinner here is genus 3. So let's see if we can generalize what we did to multiple handles. How many wave functions would we have for the toric code to store information in for a G-handled torus? Well, we have to first, instead of having a simple square lattice, we're going to use any graph spanning the surface. And maybe like this, some of them, you'll have square plaquettes or triangular plaquettes or pentagonal plaquettes possibly. And we may have vertices with 3 edges, 4 edges, 5 edges coming into them and so forth. So a more general graph is allowed. And then we are going to put spins on each edge, exactly the same way we did before. There'll be a spin on each edge. We'll color the edge red if the spin is down, and we'll color it black if the spin is up. Then we will use the famous Euler characteristic from topology. This is a picture of Leonhard Euler. Euler, I didn't realize this until I was reading about him recently. He was almost completely blind for the last 25 years of his life, during which he wrote 1 mathematics paper per week. And he said that not having vision took away distractions and he could focus on what was important. I'm not sure that works for everyone, but it worked for him apparently. Anyway, one of his marvelous topological discoveries is what's known as the Euler characteristic, sometimes known as chi. 2 minus 2 times the genus of the surface is equal to the number of vertices minus the number of edges plus the number of faces on a graph spanning the surface. Okay. This is just a topological identity. It's a fun thing to play with. If you haven't done it, but you can check that it's true. I'm just going to rewrite this by moving some of these factors around to other sides. And I'll write 2G is the number of edges minus the number of vertices minus 1 minus the number of faces minus 1. Why did I write it this way? Well, the number of edges is the total number of degrees of freedom because we put 1 spin on each edge. The number of vertices minus 1 is the number of vertex operators. We have 1 vertex operator per vertex, but then we have this 1 constraint over the entire system, which is the product of all the vertex operators in the entire system has to equal 1. That's still true. So the number of independent vertex operators is the number of vertices minus 1. Similarly, the number of faces in the system minus 1 is the number of independent plaquette operators because we have this 1 constraint that the product of all the plaquette operators should equal 1 as well. So if you take the total number of degrees of freedom and you subtract off the number of independent operators, you're left with the number of degrees of freedom, 2 times the genus. So the number of wave functions you have is 2 to the 2G wave functions. So we had with just a regular torus, we had genus equals 1 or 2 degrees of freedom or 2 squared wave functions, 4 wave functions. But if we had a 2-handled torus, we would have 4 degrees of freedom or 2 to the 4th different wave functions. And you can another way of describing this is simply saying that you can, for every handle, you can describe whether there's an even or odd number of red bonds running around that handle. Okay. Okay. So the reason why we're really interested in the toric code, particularly this year, is because the codes based on the toric code are some of the most robust and potentially practical quantum codes that are known. This is a paper, a beautiful paper that came out in Nature earlier this year by the Google Quantum AI group, where they built a toric code out of superconducting qubits with up to 21 total bits in the system. And they showed that they could do error correction, many rounds of error correction, always correcting back to the initial quantum state with very high precision. It's a really beautiful demonstration that this type of error correction really works very well. One thing that should not be overlooked is it's from Google, a very powerful large corporation, but the number of authors on this paper, the number of people that were required to work on making this thing really function is pretty close to 100. So it was not an easy experiment by any measure, But the first time you do anything, it's always hard, and then in the next iteration, it gets easier and easier. So I don't think we're at the point where we're going to say, well, everyone's going to be doing it tomorrow, but they've definitely broken the door open at this point. Okay, so let's talk about matter, about substances, phases of matter, things that condensed matter physicists are interested in. Well, we can turn this toric code into a type of matter in the following way. Remember, the toric code, we define two operators, the vertex operator and the plaquette operator, and our rules for being in the code space were that all the vertex operators should be in the +1 state and all the plaquette operators should be in the +1 state. Now, how can I make this into a type of matter? Well, we just say, let there be a Hamiltonian, like let there be light, let there be a Hamiltonian for our physical system, where the Hamiltonian is just minus the sum of all the vertex operators and minus the sum of all the plaquette operators. All these operators have only two eigenstates, +1 and -1. And so if you ask, well, and they're all commuting operators as well. If you ask, what is the ground state of this Hamiltonian? It is simply the states where all the V's are in the +1 state and all the P's are in the +1 state. If any of the operators are not in the +1 state, that's an excitation. Or another way of saying it is that puts you in the error space of the code. So when, you remember the beaver is going through, the error correcting machine is going through and checking that all these operators, the vertex operator and the plaquette operators, are all in the +1 state. And if they ever find something in the -1 state, they say, oh, this is in the error space, we have to correct it. But from the point of view of matter and Hamiltonians, we say that if we ever find a vertex operator not in the +1 state, in the -1 state, we say that's an excitation. Okay, that's not in the ground state space anymore. Okay, so in order to see this connection between quantum error correction and topologically ordered matter, we need to think about what these excitations are, or what the error space is. And let's think about how it is, or what happens when the daemon comes along and tries to create a defect or an error in our code. So here, I'm not going to draw the red bonds anymore. I'm not going to draw the up and down bonds. I'm only going to draw the results of the daemon's actions. I'm going to draw what happens due to errors. So at some point, the daemon might come along and he says, well, I want to mess things up. And the way I'm going to mess things up is by flipping over some spins. So he might apply a sigma x to the spin on this edge, to this bond. Sigma x flips over the spin on this edge. What does that do? Well, what it does is it actually, the sigma x operator anti-commutes with the two vertex operators on either end. Both of these vertex operators have sigma z's acting on this edge. So the sigma x operator anti-commutes with those sigma z's. And what it does is it takes the vertex operator that was sitting in the +1 state and puts it in the -1 state instead. To see that in a little more detail, we started in the code space, or the ground state, where the vertex operator applied to the wave function is +1 times the wave function. Then let's imagine hitting some edge with a sigma x operator. We can insert v here, because v times psi equals psi from what we have up at this line here. So that's the same. Then we anti-commute v through sigma x, and we rewrite that now as the vertex operator applied to the wave function sigma x applied to psi, the wave function after the daemon's been there, is equal to minus sigma x applied to psi. So the vertex operator value has gone from +1 to -1 at both these positions of these two red x's, okay? Now, when the beaver shows up, the error correcting machine, it will detect a defective vertex here and a defective vertex here. And then it says, okay, I found two defective vertices right next to each other. What do we guess has happened? Well, what we guess has happened is that the daemon has been here and applied sigma x. So how do I fix it? We apply sigma x again, and that just gets rid of the error. It just flips the spins back over and puts them in the initial state. So that's the basic error correction process. You bring those defects back together and you reannihilate them, and you get back to the ground state space, or you get back to the original state. You undid the error. Now, if the daemon could be rather quick and apply apply an error to this bond over here and maybe also to this bond over here, but the error correcting machine would find two defects near each other and two defects near each other over here, and it would conclude that the daemon has been there twice, and it would just undo those two errors in the same way as each other, just to reapply sigma x to get rid of the error that was just created. However, the daemon could also apply sigma x twice at two positions near each other like this. So to this bond, and then also to this bond here. Now you notice when it's applied to the second bond, it flips over the vertex operator here, putting it back in the code space, but now makes this one defective. So you can think of it as pulling defects apart from each other. First it made the defect here, and then it pulls the defective vertex out to here by flipping over both of these two vertices. So now I have sort of this error string, this blue error string from here to here. Now, when the error correcting machine comes along and looks for defective vertices, it finds a defective vertex here, and it finds a defective vertex here 2 steps away. It doesn't see this, what I've drawn here is blue. It doesn't see anything blue here. It only can measure the value of the vertex operator here and the vertex operator here. But you can be fairly clever, and you can say, well, probably what's happened is the daemon's been there twice, and I can undo that by just applying sigma x twice and getting back to the original state. And then maybe the daemon could be even faster and apply the sigma x 3 times to move the defects several steps apart from each other. And now you have a quandary. You don't see the blue line. You only see the 2 defects here, one here and one here. And you don't know if the daemon went down 2 steps and over, or over and then down 2 steps. So when you're trying to undo the error, you have to guess. One possibility is you guess correctly and you undo exactly what the daemon did, but in the opposite order, and you get back to the ground state. But the other possibility is you guess wrong and you close up this blue loop, bringing the 2 defects back together. You successfully re-annihilate the defects, but you've now made a closed blue loop of sigma x applied to the ground state space or the code space. Now, does that cause a problem? You can think of this as, so the daemon did part of this, and then we did the rest of this by trying to correct the error. Is that a problem? Well, it isn't a problem, because a closed blue loop is a product of sigma x's around the loop, which is the same as the product of the Plaquette operators enclosed. The Plaquette operators cancel on this intervening bond. It's just sigma x applied around what was there in the blue loop. But the Plaquette operators are +1 in the ground state space. So closing up that big blue loop applies +1 to the ground state and does nothing to the ground state and brings you correctly back to the original wave function that you started with. Okay, so is it possible for the daemon to actually create a real logical error? It is possible. The daemon can start creating errors and pull them apart. And if the daemon goes all the way around a handle, it's then changed the parity of the number of red bonds going around the handle, because it applied sigma x all the way around a handle, flipping over a set of spins that goes all the way around a handle, and it changes the ground state sector. That creates a genuine logical error. In this case, the daemon has won and has created a real error. So it's always sort of a battle between good and evil. Good is error correction. You're trying to bring the defects back together, and evil is the daemon trying to make an error string that goes all the way around the handle, which will flip your ground state sector and actually create a real logical error. So what we discussed so far is daemons that come along and apply sigma x to the Torah code. It's also possible that the daemon decides, well, I'm going to apply sigma z to the Torah code. That's another operator that I can apply. And the story here is quite similar. Here, you apply sigma z to a particular bond. What it does is it anti-commutes with the 2 neighboring Plaquette operators, and it puts the Plaquette operators in the -1 eigenstate on the two neighboring plaquettes. So the error correcting machine would find this plaquette is not in the ground state, and this plaquette is not in the ground state either. And again, you do exactly the same thing. Once you've detected two errors right next to each other, you say, oh, the daemon must have been here and applied sigma z. So let's just apply sigma z again on that plaquette, and it will undo the error. But the daemon can apply the error several times, and you have to decide, okay, I'm going to bring those errors back together, and I do that by applying sigma z's. One possibility is I guess correctly, and I can undo the entire path and get back to the original wave function. But another possibility is I guess wrong, and I make a closed loop on the dual lattice, if you want to think about it this way. I make a closed loop of sigma z operators on dual lattice in trying to correct this error. I successfully removed the excitations, but the question is whether I messed up the ground state in so doing. But again, this closed dual loop is exactly equal to the product of the vertex operators enclosed. The vertex operator here, 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 and here, multiplied together, cancels the sigma z operators on these 4 bonds, leave sigma z's on the light blue bonds. And if you started in the ground state space, the vertex operators are all in the +1 state. So all you did was apply +1 on the ground state. So you get back to exactly the same wave function that you started with. Again, you can create the daemon could create a genuine logical error by dragging the defect all the way around the handle. And in this case, you have this, this line, this dual line, if you want to think about it, going around a handle. And this line can now measure the parity of the spins, the parity of the number of red lines going around the vertical handle. So here it would be able to measure that there is an even or an odd number of red bonds going around the handle. And in fact, in order to figure out how many red bonds go around this handle, you have to make a measurement on basically on a path that cuts around the handle dual to that. So being able to distinguish whether you're in the in the even sector or the odd sector around the handle, if you can distinguish between the two, then you can decohere the qubit. You can apply a different phase to the part of the wave function with an even number versus odd number of red bonds running around the handle, and that also creates a genuine logical error. Now, so we've considered sigma x errors and sigma z errors. Sigma y errors are just a combination of the two of these, and any error that the daemon can apply to the system is some combination of sigma x, sigma y, and sigma z. So since we can correct sigma x and sigma z, we can correct sigma y. We can correct anything that the daemon can do, as long as the daemon isn't too fast and is able to drag the errors all the way around the handle. Now, this is perhaps the most important statement that I'm going to make, and it's a rather subtle statement, but it makes the connection between what we call topologically robust matter and quantum error correcting code. So let's think of the toric code as being a type of matter, a type of substance. When it starts with some sort of, it starts with a degenerate ground state. It has this fourfold degenerate ground state, 4 ground states associated with the 4 possible sectors of even or odd number of red bonds running around each handle. Now let's ask, what happens if you perturb the Hamiltonian a little bit? Does anything fundamentally change? Do you break that degeneracy of the ground state? And the claim is that you don't break the degeneracy of the ground state by perturbing the Hamiltonian. Those properties, the degenerate ground state and all sorts of other important properties of this topological matter remain robust to small perturbations of the Hamiltonian. Just for the sake of argument, let's imagine perturbing the Hamiltonian with some perturbation, which is just a sum of sigma x, sort of a magnetic field pointing in the x direction. but it doesn't matter what operator I use here. The statement is that the fact that that errors can be corrected is equivalent to saying that this thing is topologically robust. And why is this? Let's try to explain what that is. If I want to describe what happens to the wave function under this small perturbation, I'm going to write out a perturbation series, just do perturbation theory on my wave functions order by order. And I'll write it in terms of green functions. So I'll have Green's function times delta H, Green's function times delta H squared, and so forth and so on and so forth. Order by order, each term in this series, the new wave function, each term is written in terms of the old wave function, and each term in this series is smaller by lambda, the coupling constant, divided by the excitation gap. So there's always an energy denominator here, which is at least as big as the excitation gap. So, so we can sort of keep track of the big terms and the small terms in the perturbation series. Now, if I want to ask, is the ground state still fourfold degenerate? What I need to do is I need to basically diagonalize within the space of those four wave functions, my new Hamiltonian. These are now the perturbed wave functions under the perturbation by this perturbation series here, perturbation due to this perturbation Hamiltonian. And I want to diagonalize this this matrix element between the ith wave function and the jth wave function and the new Hamiltonian, and these wave functions are modified by this perturbation series. But the claim is that this matrix element is, first of all, is diagonal in I and j, and secondly, it's the same for all wave functions up to order lambda over the gap to the length of the torus. Why would I say this? Well, in order to connect to have an off-diagonal element of this matrix in I and j, you have to turn one of these wave functions into another wave function. You have to change the parity of the number of loops around the handle. And to change the parity of the number of loops around the handle, you have to apply lots and lots of sigma x's. You have to apply them to many, many, many different bonds. And that only happens to go all the way around the handle. And that only happens at very, very high order in perturbation theory. In fact, to order which is equal to the length of the torus. So you never get any off-diagonal terms in this expression up to very, very high order in perturbation theory. Similarly, can the value of this matrix element be different for the different ground state sectors? And the answer is it can't, because being different in different sectors means I've made a measurement of the number of red bonds running around a handle. And I know that in order to make a measurement of the number of red bonds going around a handle, I have to be able to drag one of these defects all the way around I had to take one of these Plaquette defects all the way around the handle of the torus. And again, that only happens at order lambda divided by the gap to the length of the torus. So if the coupling constant here is smaller than the energy gap by a little bit, then it's exponentially small splitting in the ground state degeneracy. So the ground state degeneracy is exponentially well protected. And this gives us what is sometimes known as a good working definition of time. I realize I'm running over, but I'll be less than 4 or 5 minutes left. So this gives us a good working definition of topological order. 1, you need to have a ground state degeneracy on the torus. 2, the matrix element between your ground states for any local operator should be, well, diagonal between the ground states plus an exponentially small quantity. And 3, this always implies exotic braiding statistics for particles. Now, that's not an obvious statement, but turns out to be true. And let's see that it is true here as well. So what we want to do, now this is sort of going back to the previous lecture, we want to think about world line diagrams with time running vertically. We want to take a vertex defect around a Plaquette defect and reannihilate them and see what happens. So let's see what happens when we do this. So first, we're going to create, we're going to apply some sigma z's to create our Plaquette defects, move the Plaquette defects apart from each other. Now over here, we'll apply some sigma x's to make some vertex defects, and we'll drag the vertex defects around the Plaquette defects like this and reannihilate. And remember that the dark blue loop, the product of sigma x's around a loop, is equal to the product of Plaquette operators enclosed. And previously we said, well, the product of Plaquette operators enclosed is +1 because everyone's in its ground state. But here it's not in its ground state. Here, there's someone who's excited inside, someone's in the error space inside that dark blue loop. So instead of getting +1 for going around that loop, we get -1 for going around that dark blue loop. And then we can, reannihilate these two Plaquette defects. And what we get is that when we braid to a vertex defect around a Plaquette defect, we get a -1 instead of +1. Now, we sort of know this idea of bosons, fermions. Well, this will be the tenuous relation to Dirac that Fermi statistics is often known as Dirac Fermi statistics. Dirac's initial paper describing fermions was, it's incredibly beautiful and incredibly modern way of thinking about things. It's really, it's no book is any better than Dirac's original paper on describing the physics of fermions. Anyway, so we know we have bosons. When you exchange them, you get a +1. Fermions, you exchange them, you get a -1. Both the vertex defect and the Plaquette defect are actually bosons, but here they're with respect to themselves. But here you get non-trivial braiding of the vertex around the Plaquette defect. So these are sometimes known as anions because they're slightly more complicated than regular bosons. We often call them bosons anyway. But anions means anything else. So here there's non-trivial braiding of the vertex around the Plaquette. You pick up the -1 sign. Okay. And also this you can make exactly the same argument that this -1 sign is topologically robust, that you can perturb the Hamiltonian and you will still get to very high order in perturbation theory, you'll get exactly -1. Okay, so to summarize the toric code, it's a code, it's topological matter, it has anions, and you can make them now. So I think I'll stop there. I'll take any questions and thank you for your attention.
Thank you, Steve, for a very nice talk about something that it's a sign of my age and probably yours too. I still remember sort of where I was when I sort of understood quantum error correction, and it was a huge shock. If there's one thing to take away from people, for people to take away, if you didn't know that this already, the idea that you can actually fight decoherence, you can fight the demon, was a huge development. Even though, as you say, it goes back to the 90s with Peter Shor. Yeah. And it's very exciting that people are realizing these.
That people are able to do this now. Actually, Peter Shor's original 9-qubit code, you can interpret that as a toric code. Actually, you can. Yeah, as a way to interpret it as a toric code, just a slightly complicated one. In my mind, I've argued this with some people with a quantum information background who insist that Peter Shor's 9-qubit code is easier to understand than the toric code. But for my money, the toric code is actually easier. Both of them are brilliant. Peter Shor deserves all the accolades he's gotten and many more for realizing that this was possible. But also Alexei Kitaev deserves all the accolades he's gotten and many more for realizing that this is really topological matter in disguise.
So I don't know if there are any questions from either, and I would say the questions going back to even just sort of the fundamental issues of quantum error correction from either faculty or students. Maybe I can start about, so I guess I should know more about the Google paper. It's did they store a qubit, or did they just simply demonstrate that they could carry out that they could have a functioning beaver, I guess is the way to put it.
They did store qubits, yes. Yeah, and in fact they're using a slightly souped up version of the, okay, so I will admit that I actually haven't read it as closely as I should either. But they're using a souped up version of the toric code with surface code. So, and they play with different configurations as well. So they're able to store multiple qubits in some cases, not just two, but more in some cases. But I have to admit that I don't know the details of the paper that well.
So I guess it's probably unfair to ask if they did any braiding of any kind, or is that still something that we're waiting for?
I think actually there was a smaller, if I remember correctly, there was a smaller toric code made a couple years ago. And I believe they claim to actually have done a braiding. I'm not sure if it was done in this page. I mean, it was a much smaller example that was done, and they had to work very hard to even get that. But I think they claim to have done the elementary braid in that older paper. And this was, I forget which group did it, but it wasn't the Google group. It was a different group. But this one was much more significant than what they did. I think they had maybe nine bits or something like that.
So let's see if
maybe I can ask a question, Nick.
Oh yes, please.
So again, thank you very much for these two wonderful lectures. And as a non-expert on the subject, and since we have many students in here, so what will be the next step, right? So what will you regard as, after your two brilliant lectures, what are some of the most important open questions that remain that people should start to, I mean, young people should start looking into and see if they can make any contribution?
So there's a lot of different directions that one can take this in. There's an enormous experimental world of trying to realize these things. Okay, so Google did this one demonstration, but there's a lot more that needs to be done. I mean, they stored, say, 2 qubits or something like that. And if you really want to do something useful with this, you have to do concatenated codes and levels upon levels of this kind of error protection. So there's just a ton that can be worried about from the experimental standpoint. But even not, you can go different directions of. I mean, one of the things that I was hoping to have time to get to, but I didn't, is that you can generalize toric code to, not that much more complexity. Instead of each leg being a single 2-state system, it can be a multiple state system where you have different colors along the different edges. And instead of being a simple, like loop gas of these red loops, there's branching loop gas where there's certain branching rules and so forth. And this enables you to do much more in principle. Hardware wise, it's much more demanding as well. So it's going to be harder for them to implement. But if you could do it, there's actually a lot more. You can start doing information processing right in the code instead of trying to externally do your. These work really well as quantum memories, but they're not so good for processing information. You can apply -1 to them, but that's not so useful to just be able to apply -1. You want to be able to manipulate your qubits in arbitrary ways. So there's that direction as well. There's a lot of other experimental systems where topological matter is being, people have talked about and realized, it may be the case that superconducting qubits is not the be-all and end-all of quantum computation or of quantum simulation. I mean, the people doing cold atoms and trapped ions are, I used to think people doing trapped ions were crazy to think they were going to be able to compete with the superconducting qubit people. Now I'm actually not so sure. I think they have quite a bit going for them. That they might, they might actually be able to not only catch up, but do some things better than the superconducting qubit people. So there's there's that, which is, really on the qubit side of things. But then there's sort of the more cold atom side of things where you're not really thinking about sewing together qubits, but more of designing a Hamiltonian, which will be in a particular phase of matter. I mean, one of the important principles here is that you don't have to, from a topological matter standpoint, you don't have to get exactly the right Hamiltonian. If you get close, you get all the right properties. It still has exactly the right properties because of this perturbation argument that as long as you can get close, you have everything you need. And so you can start thinking about, well, ideally, you think that, somewhere out there, there's some particular material, Herbert Smithite or some Kagame spin lattice or something like that, for which, you pull this thing out of the ground or out of the crucible in your laboratory, and you measure it, and you say, oh my gosh, this is the toric code. This is in the attraction basin of the toric code. It has all those properties by itself. And there's a ton of sort of condensed matter physics that can be done in looking for these or trying to engineer these, not in the sense of we're going to try to plug together a lot of qubits and design it, bit by bit, but rather we're going to try to cook up a material such that the Hamiltonian is close enough to the right Hamiltonian to give it the right properties that we want. There are some outstanding theoretical questions about topological matter. I mean, everything that I've described here is 2 + 1 dimensions. But I think you asked yesterday about 3 + 1 dimensions, and there's a lot of 3 + 1 dimensions. A lot less is known about. I mean, a lot is known, but it's not nearly as complete an understanding of topological matter in 3 + 1 dimensions. And we can again ask the same kind of questions, whether we want to think about toy model Hamiltonians that you engineer with qubits, or Hamiltonians that you just close enough that might exist in real life. So there's a huge burst of activity right now in fracton systems, which have I won't say a symmetry, but they're kind of closely related to some of these topological systems like the toric code, but they have some really interesting properties when you start looking at their excitations, that the excitations are inherently pulled back to each other. They sort of fundamentally want to reannihilate, or they're constrained in certain special ways. And so there's a lot of interest in that theoretically and less experimentally, because we don't know exactly where to look for these in experiment right now. But there's an awful lot of good directions that a young person can go into in this field. And if you let's see, if you go all the way back, if you're interested in this field, you can read my book down here on my webpage. Go to the course 2021, Topological 2021, download the newest version of the book, and it's good bedtime reading, and let me know if you find mistakes.
Thank you.
Yeah, I won't even force you to buy the book because it's free right now until it's published.
So maybe I see Toby.
Hi, thank you for a nice talk. I feel like I will have more questions after I digest lectures, but for a moment I have maybe a bit technical questions about perturbation. So you mentioned like a simple example of the perturbation of the Hamiltonian, right?
Yeah.
So I'm just wondering, like, it seems like the error correction is really important, but so if this, let's say, magnetic field is already complicated, like individual, like it's not uniform.
Sure.
But like a microscopic level. And
yeah.
So this is like considered to be unlikely to happen, or
no? That's perfectly okay.
Okay.
I just used the example. Let me see if I can go back to that page. I use that example just because it's sort of simple to think about. But it doesn't matter what the perturbation Hamiltonian is, as long as it is a local operator. So any combination of local operators will have the same property. The point is, as long as you need a macroscopic number of them to drag a defect around the handle, then you're protected from them. That things like the ground state degeneracy cannot be destroyed by the perturbation Hamiltonian. It's like the daemon can show up and can start applying different different types of operations, and we can correct them all, bring them back together, as long as the daemon isn't fast enough to take them all the way around the handle. Similarly here, the perturbation can be any sum of local operators. They don't have to be uniform. They can be different from site to site. They can be sigma x, sigma y, sigma z. It doesn't matter. As long as it's a local operator and you require a macroscopic number of them to drag a defect all the way around the handle, and that allows you to connect one of these ground states to another, and allows you to distinguish the ground states from the other. But if you can't get a defect all the way around the handle, you can't distinguish the ground states from the other, and you can't connect the two ground states from the other. And then the ground state degeneracy is protected. And by a similar argument, the braiding phase is also protected. As long as you braid at rather large distances, you would need to, if you braid particles around each other at a distance L, then the braiding phase is protected up to order lambda divided by the gap to the power L.
So if I understand right, so it looks like in each site I can have random sigma
Sure.
to have a Hamiltonian, and then but still it should have a small lambda, right? I think because
so lambda, if lambda is too big, then basically then the perturbation series doesn't converge. If lambda is bigger than the gap, then you're dead. So I mean, you have to be a little bit more careful than just saying, look, everything is smaller by lambda divided by the gap, because in fact, as you go out in the perturbation series, they get more terms too. So you're adding up more terms in each successive power here. So you have to be a little bit more careful to show that this perturbation series converges. But if lambda is big enough, then you can prevent the series from converging. But if lambda is small enough such that it converges, then you're okay out to this order.
Okay. Thank you.
Welcome.
So I'm gonna make one last attempt to see if there are any students who have questions.
Please, students, ask me a question.
And it's possible the subject of this lecture might be somewhat intimidating, but I think Steve will also be happy to answer questions about yesterday's lecture. And I know some students have them because they came to me and asked some questions. So just to see if anyone has any.
So a lot of
student.
Oh, okay.
Yeah.
Yeah, so a lot of this was shown using just like a two-dimensional square lattice, right? So how do things change if you consider different geometries and stuff like,
good question. Let's see. So basically the answer is it doesn't change at all. Well, okay, as long as you're in 2 dimensions, a two-dimensional surface, everything is almost entirely unchanged, basically because of this Euler argument. You just need to guarantee that your vertex operator has to insist on an even number of bonds coming in, even number of red bonds coming into each vertex. That's the only thing you have to do. The Plaquette operator has to flip over the edges of the plaquettes, and it can be even an irregular graph, an irregular, what you call an irregular lattice, although the terminology probably shouldn't call it a lattice. So in 2 dimensions, it's completely unchanged as long as it's a 2-dimensional surface, and the genus is the only important thing there, whether one handle, 2 handle, 3 handle, so on. Now you might ask, can I do this with a 3-dimensional lattice, where maybe a 3-dimensional cubic lattice or something more complicated like that? And the answer is you can. You can start thinking about toric code or other similar models in 3 dimensions or even 4 dimensions. The properties, some of the properties are similar, and some of the properties are a little bit different. So the vertex defects in 3-dimensional toric code are quite similar, but the Plaquette defects are no longer points, but they're like fluxes, and in fact, we even drew them like they were fluxes. Where was this? Yeah, here. Okay, hold on, let's see if I find it. Yeah, here. So we drew a little X through the plaquette for a for a plaquette defect. Really, you should think of that as being a flux through the plaquette. And in a three-dimensional toric code model, those fluxes have to go somewhere, and they have to sort of snake their way through the cubic lattice. And so you get interesting situation where you can talk about you get a -1 phase for taking a point-like vertex defect and passing it through a loop of flux defect. So you can get much more complicated braiding properties in the three-dimensional toric code. So that's certainly been studied and discussed quite a bit. And you can, there's lots of generalizations of the toric code in a higher dimension as well.
So it's like three-dimensional toric code. Is that something we can like experimentally realize? Like, because at least in 2D, right, we have periodic boundary conditions, but we need a third dimension to access that periodicity, right?
Yeah. So when we talk about experimentally realizing, the biggest challenge for making it 3D is just that you're going to need more bits. That the size of it is going to be, if you want a 2 by 2 by 2 lattice in 3 dimensions already requires 8 bits, and 3 by 3 by 3 already requires 27 bits. So that's already pushing it. Whereas in 2 dimensions, you can get away with less. The periodicity actually isn't so much of a problem because in the physical system, the actual physical position of the bit isn't really important. It's really the wiring. At least if when you talk about assembling this from transmon qubits, really what you're talking about is how you've wired the qubits together, who's connected to who, and the actual physical position of it doesn't matter. So you could simulate a three-dimensional model even if all of your qubits lived in a plane.
Oh, okay, cool. That makes sense.
Yeah. Of course, it's going to be, the plane is going to have to get bigger rather rapidly. But I guess they can handle that up to a point.
So I actually hesitated for quite a while.
Hi, Kun, how are you?
Hi, Steve. Good to see a wonderful lecture that really learned a lot. So in the spirit of helping the students, maybe I should point out that there is a section in the book that I published with Steve Gerving, which actually is used here as a textbook for condensed matter physics. Actually, just checked, we actually used the same tradition. Well, it's not a tradition, but it's actually a choice that we use sigma z for the vertices and the sigma x for the plaquettes. So one thing which may help the student the most is I would like to point out that Steve just gave away the answer to the last problem after the section for homework, which is to generalize this 2D, 3D toric code to 3D. So this is actually related to Jorge's question both today and yesterday. And as Steve pointed out, when you go from 2D to 3D, some of the point excitations become line excitation, loop excitations. So that's the main point of that homework. So that homework is no longer useful, at least here at FSU. Okay, well, I apologize for giving for spoiling. It's a beautiful book, incidentally, I'm not sure. To tell the truth, actually echoing what Nick was saying. So actually got reminded a lot about the toric code because I forgot most of it already, as a matter of fact. Because it is not so intuitive. It's subtle. It's of course absolutely beautiful. So thank you. You're welcome. I'm glad that you guys are teaching that. That's great. Actually, I didn't. I don't know if Oscar, who is teaching that course now, covered it, but it is in the book. It's actually quite detailed. I'm actually even surprised. I have 9 homework problems after that section. That's probably more than some of the whole chapters, as a matter of fact. And the last one, which has a double star, a double bending line, meaning it's extra challenging, is generalizing it to 3D. Yeah, well, that does sound like a. Actually, it's boy, I'm now tempted to steal that problem and put it in my book too. But I have your permission, so maybe I'll do it. I'm trying to come up with good problems from places, and usually as I go along, I sort of think, oh, that would be a good problem, and I add one in. But I hadn't even thought about the 3D toric code because the book is so 2D focused. But it's a good
good question indeed. So,
If there are any students in my quantum computing class here, I will be doing quantum error correction, though my plan is to do the 9-qubit, the Shor 9-qubit code and not the toric code. But if there's sufficient demand, I'll be happy to do the toric code, and you can probably guess what one of the homework problems will be.
right. And you can show how they're really the same thing also.
Yeah, I might do that.